Hello, this video is about the Nobel Prize in Physics for the year 1914, awarded to Max von Laue for his discovery of the diffraction of X-rays by crystals, an important step in the development of the X-ray spectroscopy. We will give first some information about what he did, some biographical information, and then the awards ceremony speech. And in the next video we will deal with his Nobel Prize lecture. Here you see, by the way, some illustrations made by von Laue or one of his collaborators in the original 1912 article. Here you see what equipment he used. That's information about what he did, coming from the official Nobel Prize site. A phenomenon known as diffraction patterns occurs when waves pass through small, tightly spaced openings in a screen. In 1912, Max von Laue came upon the idea that X-rays passing through crystals might create similar patterns. That is, that the crystal structure would correspond to the openings in the screen. Experiments confirmed von Laue's idea. This demonstrated that X-rays could be described as waves. The method also made it possible to use diffraction patterns to determine crystal structures. As I said, this is from the original official Nobel Prize site. Here you see the link. There's some biographical information also coming from that site, but summarized by me, so a bit shorter than on the site. Apart from his early work, already mentioned, von Laue's scientific work extended over a wide field. Early in his career, he was greatly excited by Einstein's theory of relativity, and between 1907 and 1911, he published 8 papers on the application of this theory. In 1911, he published a book on the restricted theory, I think that is meant the special relativity theory, and in 1921 another on the general theory, both books getting into several editions. His best known work, however, for which he received the Nobel Prize for Physics for 1914, was his discovery of the diffraction of X-rays on crystals. This discovery originated, as he related in his Nobel Prize lecture, when he was discussing problems related to the passage of waves through periodic crystalline arrangement of particles. The idea then came to him that the much shorter electromagnetic rays, which X-rays were supposed to be, would cause in such a medium some kind of diffraction or interference phenomena, and that the crystal would provide such a medium. Although his colleagues Sommerfeld, W. Wien, and others, with whom he discussed the idea on a skiing expedition, raised objections to the idea, W. Friedrich, one of Sommerfeld's assistants, and P. Knipping, tested it out experimentally and after some failures succeeded in proving it to be correct. Von Laue worked out the mathematical formulation of it, and the discovery was published in 1912. It established the fact that X-rays are electromagnetic in nature, and it opened the way to the later work of Sir William and Sir Lawrence Bragg. Subsequently, von Laue made other contributions to this subject. Also prominent in von Laue's work were his contributions to the problems of superconductivity. As said, this is summarized. When you want to read the original complete text, you have to follow this link to the official site. Here again, you see some illustrations coming from the 1912 article. Here you see some interference patterns, probably made with X-rays through crystals. Here it is Röntgenstrahlen. That's German for X-rays. And here again, some of his illustrations. Then we go to the award ceremony speech by Professor G. Grandfist. I don't think this speech was really spoken. It was during the First World War, so it was probably more of a press communique. Again, this is summarized by me. So if you want a complete text, then you have to go to the original site, official site. Here we go. Not even the strongest magnetic fields were able to alter the direction of the rays. It was equally impossible to prove the existence of refraction. If the X-rays are of a corpuscular nature, particles, they would not therefore be carriers of an electrical charge, as is the case with other known rays of corpuscular nature. If therefore we wish to disregard matter which has no electrical charge, it is necessary to assume that the particles bear two charges of opposite sign, one of which neutralizes the other. On the other hand, from the fact that there was no evidence of reflection of X-rays, it was possible to assume that, should they consist of a transverse wave motion, the relative wavelength would have to be very small. As for very small wavelengths, according to the theory of dispersion of light, the refracting index would approach unity. This impulse was believed to consist of disturbances which occur in the ether when the cathode ray particles is impeded on colliding with molecules of matter. This disturbance or impulse was believed to propagate in all directions at the speed of light from the ether surrounding the electron. In each part of the space, this disturbance was maintained for a period of identical duration to what in which the electron was impeded. This period of time multiplied by the speed of light was described as the impulse width, a quantity, if the nature of the X-rays were the same as that of light rays, would coincide with the wavelength. According to that theory, the X-ray impulse, which originates perpendicular to the cathode ray bundle by which it is excited, is alleged to be completely polarized. The evidence of this type of polarization was first produced by Barkla in 1905, but contrary to the theory, the polarization was not complete but only partial. Not adequate to prove the existence of a transverse undulation, once Dorn had succeeded in 1897 in determining the fraction of the energy of the impeded electrons, which is converted to X-rays. W. Wien was able to calculate the impulse width according to these figures amounted to approximately 10 to the power minus 10 centimeter. The short impulse width thus determined could explain the lack of success with previous diffraction tests which had been carried out on slits with X-rays, for even with the narrowest slit, the diffraction phenomenon which is produced by such small impulse widths or wavelengths would have to lie just about the limit of the possible observation. Even of the most accurate of these tests conducted by Walter and Paul, that they refer diffraction highly probable, it would meanwhile seem to follow that the upper limit for the impulse width of X-rays lies at 4 times 10 to the power minus 9 centimeter probably. It's not in the text, but it's probably centimeters. This was a situation when von Laue placed the research medium of the highest import at the disposal of science by virtue of his epoch-making discovery of the interference of X-rays, and at the same time proved that X-rays, as is the case with light rays, consist of progressive transversal waves. Previous research had indicated that it was highly probable that, if X-rays are wave motions of the same type simply as light rays, then the wavelengths would have to be in the order of 10 to the power minus 9 centimeter. In order to obtain clear interference phenomena of the same type as those which are caused when light rays pass a grating, it was necessary for the distance between the grating slits to be in the order of 10 to the power minus 8 centimeters. But this is approximately the distance between the molecules of a solid body, and it was in this manner that von Laue arrived at the idea of employing as a diffraction grating a solid body with regularly arranged molecules, with other words, a crystal. As early as 1850, Bravais had introduced into crystallography the assumption that the atoms composing the various crystals are arranged in regular groups, so-called three-dimensional lattices, or space lattices, whose constant could be calculated with the aid of crystallographic data. However, the theoretical basis of space lattice was unknown, and thus it was first necessary for von Laue to develop this theory, if else the investigations were to have a value. This he did mainly according to the same approximations as those conventional to the science of optics as applied to the normal one-dimensional lattices. Von Laue left the execution of the experimental work in the hands of W. Friedrich and P. Knipping. The apparatus which they employed consisted of a lead box into which they admitted a thin bundle of X-rays, which they directed so far as to fall upon a precisely oriented crystal. Sensitized film was positioned both behind and at the sides of the crystal. Already the preparatory tests showed that the intensity maxima which had been anticipated by von Laue became evident in the form of blackened spots on the film positioned behind the crystal. From the grouping shown by these intensity maxima in accordance with the requirement of the theory as established for such photograms of various crystals and from the degree of clarity with which they have been reproduced, it follows that they are an interference pattern. Absorption tests have shown that the rays which give rise to the points of interference are actually X-rays, and from this von Laue has deduced with a high degree of certainty that the X-rays which cause intensity maxima or irradiation of a crystal have a character of a wave motion. However, the same is required also for those rays employed for irradiation purposes, for, as he says, were they of corpuscular nature, coherent oscillation could only arise from those atoms set in motion by the identical corpuscle, and these atoms would have to form together one whole agglomerate whose dimensions would be largest in the radiation direction. However, contrary to this was indicated in the experiment. This would result in intensity maxima consisting of irregularly concentrated circles. As a result of von Laue's discovery of the diffraction of X-ray crystals, proof was thus established that these light waves are of very small wavelengths. It is now possible to determine the position of atoms in crystals. It is thus rendered likely that experimental research into the influence of temperature upon diffraction will provide a solution to the question of zero-point energy, or will at least be of some assistance in arriving at a solution to this problem, as the temperature factor assumes a different value according to whether a zero-point energy exists or not. Well, this is the summary of the press release, as it was called, which was given out because in that year there was no award ceremony during the war, and next week's lecture given by von Laue was only given years later. I believe it was in 1920. We'll see that next week. More information on the Nobel Prize site is a little text called Perspectives. I have not dealt with that, but you can follow the link if you want to read it. It's quite interesting. Well, as a conclusion, still some of the illustrations from the original article. Here you see in that the interference patterns from Röntgenstrahlen X-rays, which were led through crystals. Well, this is it for the moment. As said, next week we will deal with the Nobel Prize lecture given by von Laue about, of course, this subject. For now, thank you for watching, and maybe until another time.